Welcome to a lesson on Big-Theta notation. Asymptotic notation is used to express and compare the growth rate of functions. In our case, the functions will typically represent the running times of algorithms. We will define the asymptotic notations in terms of non-negative functions, since the running time of an algorithm is always non-negative. We will focus on the notations most commonly used in the analysis of algorithms, which are Big O notation, Big Omega notation, and Big-Theta notation. This lesson will focus on Big-Theta notation. Asymptotic notation allows us to express the behavior of a function as the input approaches infinity. In other words, it is concerned about what happens to f of n as n gets larger, and is not concerned about the value of f of n for small values of n. And now let's talk about Big-Theta notation. For a review, recall that Big O notation is a notation used to express the idea that one function is an upper bound of another function. Big Omega notation allows us to express the opposite, that one function is a lower bound for another function. Our third notation, Big-Theta notation, allows us to express the idea that two functions grow at the same rate. Before we look at the formal definition, let's assume we have a function f of n, this function here in the middle, where for n greater than or equal to n sub 0, c sub 1 times g of n is less than or equal to f of n, and c sub 2 times g of n is greater than or equal to f of n. Notice we can say that f of n is bounded below by c sub 1 times g of n, and bounded above by c sub 2 times g of n. And now let's define Big-Theta notation. Let f and g be non-negative functions. We say that f of n is Big-Theta of g of n, written as f of n equals Big-Theta of g of n, if and only if there are positive constants c sub 1, c sub 2, and n sub 0, such that c sub 1 times g of n is less than or equal to f of n, which is less than or equal to c sub 2 times g of n, for all n greater than or equal to n sub 0. It might make more sense to read this as f of n is greater than or equal to c sub 1 times g of n and less than or equal to c sub 2 times g of n. If f of n is Big-Theta of g of n, f of n grows at the same rate as g of n. In other words, g of n is an asymptotically tight bound, or just tight bound, on f of n. Let's take a look at a proof. We want to prove that n squared plus 5n plus 7 is Big-Theta of n squared. When n is greater than or equal to 1, we can state that n squared plus 5n plus 7 is less than or equal to n squared plus 5n squared plus 7n squared. Notice this came from replacing 5n with 5n squared and 7 with 7 squared. And 5n squared is greater than or equal to 5n, and 7n squared is greater than 7 when n is greater than or equal to 1. And because we have like terms, we can add 1n squared plus 5n squared plus 7n squared is equal to 13n squared, and therefore we can also include this is less than or equal to 13n squared. In fact, the important part here is that n squared plus 5n plus 7 is less than or equal to 13n squared. We can also state that when n is greater than or equal to 0, n squared is less than or equal to n squared plus 5n plus 7. From here, we can combine these inequalities to state that when n is greater than or equal to 1, n squared is less than or equal to f of n, which is n squared plus 5n plus 7, which is less than or equal to 13n squared. And this is what we needed to show. Notice we have 1n squared on the left, and we have 13n squared on the right. So n squared plus 5n plus 7 is Big-Theta of n squared by definition of Big-Theta, with n sub 0 equal to 1, and c sub 1 equal to 1, the coefficient of n squared, and c sub 2 equal to 13, the coefficient of 13n squared. Before we go, let's look at this graphically. In red, we have the graph of the given function f of n. In blue, we have the graph of c sub 1 times g of n, which is 1n squared, which is the lower function. We also have the graph of c sub 2 times g of n, which is equal to 13n squared, which is the upper function. Notice for n greater than or equal to 1, c sub 1 times g of n is less than or equal to f of n, and f of n is less than or equal to c sub 2 times g of n, which is why f of n is Big-Theta of n squared, and we can also state that f of n grows at the same rate as g of n, and g of n is an asymptotically tight bound on f of n. I hope you found this helpful.